Welcome everyone to this week's ITC Colloquium. It's a great pleasure to welcome Yuri Levin from the CCA. Yuri got his PhD at Caltech, working already back then on gravitational wave detection with LIGO and on neutron stars, and especially also magnetic fields in neutron stars. He later moved on to, I think, Berkeley and CETA, then later as an, I think, equivalent to an assistant professor at Leiden, then to Monash, also become an associate and full professor, and in 2017 transitioned to Columbia University and then to the CCA, where he's a group leader right now. And he will be talking about magnetic crust-core coupling in neutron stars.
Okay, thanks very much for inviting me here. I think last time I was here was like 15 years ago. So it's nice to be back. I know you guys have crazy amounts of talks. I looked at your schedule. I don't know how you can keep up with all of them. Now mine is meant to be very informal, so please stop me at any time. I don't have to finish it. There are two topics that I want to discuss. I want to talk about the glitch in Vela, which was recently observed in 2016. I think it's very interesting. And then I want to talk about a subject which is by now quite old. These are quasi-periodic oscillations seen in magnetar flares. It's old, but it's quite dear to my heart, and recently there's been some interesting developments, so I want to tell you about this. Now, I don't know if you can see this beautiful picture of solar corona taken by trace satellite and ultraviolet. Can you see it? Can you see the picture? So I think this picture contains almost all of magnetohydrodynamics that you need to know in general and that you need to know to follow this talk in particular. So first of all, you can see the field lines, right? And you can see the field lines because plasma is stuck to them. So this is one thing in magnetohydrodynamics. So the magnetic fields and plasma are moving together. And if you look at the shape of these field lines, they're quite smooth. So that means that they have tension. So this is another feature. You know, the field lines, they're tense, they like to be straight, but they're not straight. Okay? They're bent. And they're bent because even though they like to be straight, each individual field line likes to be straight, they repel each other. There is a certain magnetic pressure, so that makes it into a bent and smooth shape. Okay, so these are three ingredients of magnetohydrodynamics that are necessary to understand it, is that conducting fluids and field lines move together. Field lines have tension, and they also have pressure. And people who look at the sun, they look at pictures like this, and they want to, or some of them want to understand what has to happen inside the star in order for the outside to have this beautiful corona-like structure. So this is what I will try to do today with neutron stars. I will try to make inferences about what we see outside of neutron stars, about the magnetic fields, magnetic field structure inside the neutron stars. So, I should say that this work is done in collaboration, quite intense collaboration with a PhD student at Columbia called Ashley Bransgrove and Andrei Beloborodov. This is about Vela glitch. And then the work on magnetar QPOs was done in collaboration with Martin van Hoven, who was a PhD student of mine at Leiden, and also later with Daniela Huppinkotten and Anna Watts in Amsterdam. Magnetic fields are very important for neutron stars, and so this is the most kind of important zoological diagram for neutron stars. You see all kinds of known to us neutron stars plotted. On the x-axis we have the rotational period, on the y-axis we have the rate of change of this period with time, and drawn in this kind of slashed nearly horizontal lines are lines of constant inferred magnetic dipole. So you see the huge range of inferred magnetic dipole fields from 10 to the 8 and even less Gauss for some of the neutron stars in the binary, probably the ones which have undergone periods of accretion, all the way to 10 to the 15 Gauss. This is in the upper right corner. These are magnetars. And magnetic fields really determine, to a large extent, what the star is as an astronomical object. Not so much, the internal structure of a neutron star, but really from the point of view of how neutron stars appear as astronomical beasts. The magnetic fields are really quite central. So not only they are central, but they are also engines for some stars. So for example, for magnetars, just like the sun, they're very magnetically active. So here is my favorite diagram about the magnetar SGR 0501 plus 4516. Now what you see here is the pulse shape in X-rays at different epochs. Actually, do I have a pointer of some kind? I think maybe this one. Okay, so this is the shape in different bands at some particular time, and then half a year later you have a completely different pulse shape in all bands actually. So this is what magnetars do. Their magnetic field breathes. It's a live thing. And we also can see clear signatures of outbursts. So this is an example of an outburst in another source, which has lasted several months. And clearly this outburst must be powered by magnetic field. So there is a nice diagram illustrating the power of magnetic fields to create emission from neutron stars in this nice paper by Vigano et al. From 2013. So what we have plotted here is a variety of thermally emitting neutron stars. On the y-axis you have their age. On the x-axis you have their age. On the y-axis you have their thermal luminosity. And you have theoretical cooling curves, two types of cooling curves for two different types of envelopes. The details don't matter. What matters is that a large amount of stars lie above these theoretical cooling curves. Now, these cooling curves are made with the assumption that there is no extra source of energy inside a neutron star. So I think the argument is quite strong that you in fact need an extra source of energy for powering these neutron stars. And so all of these magnetars here clearly are powered by magnetic fields, and presumably most of the stars here as well. Okay, so I think this is quite a convincing phenomenological argument. Okay, if you are convinced that magnetic fields and their dissipation is interesting, that means that we have to know what do they look like inside a neutron star, right? Right? So, I mean, if you're not interested, you can just leave. But if you are interested, you should stay. Okay? Because Vigano et al., this is just the start of their paper. Then they actually do the whole model of how magnetic fields are dissipated inside neutron stars, and they consider several different initial conditions for these magnetic fields. Now, look at this crazy initial condition, right? So in this initial condition, remember, a neutron star has like the outer crust, which is very thin, only 1 kilometer, and then the bulk of the star has a size of 10 kilometers. Now, in the initial conditions here, magnetic field, okay, there is a dipole outside, but once the field line enters a neutron star, it's not allowed to go into the core, it's forbidden, right? It has to travel through the crust, and then they kind of bunch really, really close together. So that means that there are huge currents, okay? If you want to bunch field lines so close together, that means there are huge currents in the crust, okay? And then they come to the other side of a neutron star, exit, and join the dipole.
Is it not allowed because of superconductivity, or why is it not allowed to enter?
I don't know any physical reason why it wouldn't be allowed to enter, but this is the initial condition that they considered. I think their motivation for doing this is that because people don't really know how to evolve magnetic fields inside in the core, because the core is complicated, it's probably superconducting. I'll talk about this a bit later. And the crust, on the other hand, the processes which dissipate magnetic fields in the crust are completely understood. So there is ohmic dissipation, there is Hall drift. And we can model this on the computer. And by saying we, I actually mean myself as well. I can do this kind of models on the computer. I'll show you in a second. Yes?
The electrons aren't available to supply a current? No, it's superconducting.
So in principle, they're completely available. There is plenty of electrons in the core. But these people censored themselves and restricted these field lines to be in the crust. Okay? Just because how the dissipation works inside the core is not... I'll talk about this a bit later. They've also considered other models. So these are other models that they've considered. But the field evolutions that they have demonstrated showed preference for this particular model. They said if you want to explain observations, okay, this is preferred. All right. Now,
Sorry, and what the term was the thickness of the lines that you say, like, you just said that there should be like a 1 kilometer, you know, the thickness of the line for this dipole initially.
This shell is the crust. You know, it's a solid crust of a neutron star. Am I answering your question?
It comes from neutron star structure.
It's just lower density where you understand the physics of that.
So this is you know, the level of our lack of understanding increases as you go from the surface inside the neutron star, and which is complete lack of understanding at the very center.
By our understanding.
I got that.
Okay. All right. So these are good questions. I'll talk more about all of these things as we proceed. I mean, these are exactly the questions that I'm looking to answer myself. Okay. So it's interesting that they prefer this model, but you know, as free-thinking citizens, we can you know, test this and question this. And so what I want to show you is that actually this is the magnetic field evolution in their model where I thickened the crust, okay, artificially. So this is how the field evolves. And you can see it really is a dramatic evolution. So it's clear why they like it, because the field finds it quite easy to dissipate. And after 2 million years, basically all the field is gone and released its considerable energy as X-rays and stuff like this, okay? Whereas if you consider now the evolution of the field in the core, this is the simulations that we did as well, actually we did for the first time, then the evolution is much slower. So, you know, you need something like 50 million years for the field to dissipate. And you can understand why. It's because in this model, all the current is really strong and it has to be concentrated in the crust. Whereas in this model, the actual dissipation happens here at the bottom of the crust where you see this gradient of magnetic field, but the field evolves much slower. So what happens in these simulations is that the fields in the core are maximally dissipative in a sense. So we allow for the field lines to adjust to whatever the field lines in the crust want to do. So they keep the... say this again? This one? They come naturally from this simulation. But what happens is that, as I said, these field lines, they have tension, right? So in principle, in the core, if you allow them to be straight, they like to be straight. But there is an ohmic dissipation, the Hall drifts, which take place in the crust. And so this type of structure of the fields is naturally occurring. So these Caspi features are smeared out if you let this run. So you see they become kind of smooth here, but nonetheless, most of the dissipation happens here at the base of the crust, and it's quite slow. Yes?
How do you define the inner edge of the crust? So if you see that under that field that the crust moves inward, how do you, I mean, what's the physical properties of the crust versus the interior, like at the boundary?
So inside the crust, the evolutionary processes are ohmic dissipation and Hall drift. And inside the core, we have magnetic field lines which like to be straight, so they're mechanically trying to straighten out. So, but the core is a fluid. Magnetic field lines mechanically try to straighten out, and they feel a certain resistance. And we can control this resistance, this mechanical resistance in our simulations. Okay, so these are two different, very different things, right? Now, so the question is there a field which penetrates into the core? So is there a poloidal field at the crust-core interface? And what I want to convince you is that in principle you can probe this by seismology, right? So remember I said to you that the field lines have tension. So that means that if the crust moves and you have poloidal fields at the crust-core interface, and the core will also move. So seismologically, it's possible to probe the presence of these poloidal fields at the crust-core interface. So now I want to talk about Vela. Vela, actually, let me see if I can. So Vela is one of the brightest pulses in the sky and one of the first ones which were detected. And so this is what the pulse looks like if you look at it from the Parkes telescope. You see these pulses are extremely sharp, extremely well defined. And the frequency of rotation of Vela pulsar is 11 Hertz. Okay, so I will stop here. Now, there is a group in, well, actually, let me back up. So one of the most remarkable things which was observed for the first time in Vela in 1969, remember this is not long after the discovery of pulsars, was that the rotational period, which was tracked by these two people, has made a jump. Okay, so it was evolving in this way, and then it jumped to a shorter value, and then it was evolving this way. So this type of behavior is called a glitch, and there is a certain history of glitches which have been observed in Vela. Okay, so it's a sudden change in spin frequency, and the origin of these glitches is interesting, but it's not what I'm going to talk about today. Okay, but let me just say that people think that, right? People think that there is a superfluid in the inside neutron stars, and this superfluid is allowed to rotate at a slightly different rate than the rest of the star, because the superfluid vortices are pinned inside the neutron star, and then when the vortices become unpinned, the superfluid and the rest of the star come closer to co-rotation. So in the process of this, the visible part of the star spins up. So there are some ideas for where these glitches are coming from. These ideas, I would say, are not certain and not completely worked out. But that's not the topic that I want to focus on today. So what I want to tell you today is a remarkable observation which was done 3 years ago. So you know how I showed you what Vela looks like in Parkes. And it would be wonderful if you could just take Parkes telescope and point it at Vela and don't do anything else with it, right? And watch it. But you can't, because there are other people that want to use Parkes telescope for, completely uninteresting projects, but, you still have to give them time. So, however, there is a small group in Tasmania which had their own telescope on Mount Pleasant, and they had complete control of what they do with it. The telescope is half the size of Parkes. It's only 30 meters. So it's only a quarter of collecting area. So it's not very sensitive, but it was theirs. And they decided what to do with it is that they'll point it at Vela and not do anything else. Just watch Vela for many, many years, okay? And see what happens. This was like a remarkable, brave thing to do. So, and in particular, this gentleman, Jim Parfyman, he decided to devote his PhD basically to this project. And he got lucky. They saw a glitch. So it was a glitch which was extremely, so you have to understand, these people measured every single pulse of Vela. Okay, these are not very good measurements. This is not very sensitive, but sensitive enough. They still could see every single pulse. So, and they saw that the rate of rotation changed. Okay, so these are timing residuals. You can see the change in gradient of timing residuals. And this is what they saw, like you could fit a straight line right here and here. You can find the point of intersection with some error. The error is about 20 seconds or so. And then they can inspect visually all the pulses. I mean, of course, they can visually inspect even more. But in principle, you can just visually look at the pulses. So here they are. They are numbered, 72, 73, 74, etc. 72, 73, and 74 look completely fine. And so does 75. 76 is very unusual. It's very broad, okay, compared to what normally Vela pulses are. And you will never find another pulse like this. And 77 is completely missing. There is nothing. So it's quite a dramatic, I mean, for somebody, you saw how good those pulses were, right? They're really, really precise. So this is, even though it seems very quick, but this is extremely significant event. The fact that this pulse is missing, and the fact that it's missing exactly in these 20 seconds where you can time this intersection of these two lines to be, I think this is very significant. It has to be taken very seriously. So, okay, what happened? Why is this pulse missing? So I'm going to present to you an idea that we worked on for the past year or so. And maybe this idea is wrong. I'm not insisting that it's right, but I think it's logical at least. So the idea is that, okay, I told you that whatever theorists think about the glitch, the origin of the glitch, this is something that happens deep inside the neutron star, either in the deep crust. Some people think maybe it's in the core, okay? But it's really hidden deep inside. The fact that the pulse is missing, one pulse is broad, then one pulse is missing completely, and then it comes back to normal, okay? That means that you have to disturb magnetosphere. So how do you disturb the magnetosphere? By something which happens deep inside the star, okay? So the only logical possibility that I see is that there is a quake. There is some kind of, catastrophic change of stress. Maybe it's local, whatever, but it drives a quake. So, okay, so let's assume that this is the quake that also unpinned the vortices inside the neutron star. Okay, and then the vortices do their own glitch thing, whatever superfluid theorists do. But I'm interested in the consequences of this quake. Now, what this quake does is that the seismic waves, they propagate in the crust, and they propagate in all directions, but in particular, they propagate towards the surface. Of course, the density becomes much smaller as you approach the surface, so the amplitude of the wave has to grow. But remember, you also have magnetic field lines. The field lines are frozen into the crystal, okay? So the field lines start to shake, and then when the seismic wave gets towards the surface, you launch alpha-wave waves, okay? You launch alpha-wave waves into the magnetosphere. What also happens, and that's important, is that, magnetosphere is quite light. So the amount of energy in the seismic wave that goes into the magnetosphere is not very big. The transmission coefficient is actually quite small. Most of the wave returns back to the crust. Not so at the crust-core interface. If there is magnetic field, if there is a poloidal part of the field here, all right? Let me back up. If we gun it over right and there is no poloidal field, nothing happens at the crust-core interface. The wave turns around and goes back to the magnetosphere, okay? But if there is a poloidal field here at the crust-core interface, then you also launch half-wave wave into the core. And these waves are heavy. They drain energy really quickly. And that turns out to be important. Now, once you launch half-wave waves into the magnetosphere, you get gradients of magnetic field because these waves, they're not the same exactly on all field lines. Some field lines are shorter than others. The waves get dephased. You get gradients of the magnetic field, so you have to have currents, okay, to support those gradients. But you are limited by the amount of charges that you have in the magnetosphere, okay? If you don't have enough charges, you can't, the charges can't go faster than the speed of light. So you actually have a natural limit to how much current you can have in the magnetosphere. If you exceed this limit, that means that you have to, your gradient of B has to be created not by the current, but by the rate of change of electric fields. So you have to grow electric fields, and they are unscreened. Now, if you have electric fields which is parallel to magnetic field lines, this is very dramatic for a pulsar, because then you accelerate electrons along the field lines. These electrons immediately produce gamma rays, right? At those crazy relativistic systems, that's what happens. You have curvature radiation. The gamma rays interact with magnetic fields. They make pairs, etc., right? It's a complete catastrophe. If you short circuit the gap that makes a pulsar, the pulse disappears. Okay? So the idea is that, once you launch strong offline waves into the magnetosphere, you flood magnetosphere with pairs, and the pairs short circuit the gap. Okay? Now, if this continues, this is bad news, because then the pulse disappears for a long period of time. That's not what we see. We see that the pulse disappears for a short period of time and then appears again. That means that whatever elastic energy you put in the crust, you have to drain it. And the only reasonable way of draining it is by converting them into the core of wave waves. There is no other efficient dissipation mechanism for the elastic waves which are sitting in the crust. After that, magnetospheric waves damp by some mechanism which we haven't worked out, and then the pulsar is back home. So these are the proposed stages for this scenario. And in orange, you see the stages that we have worked out in some detail, okay? And in black are this is the homework for you, to think about these other things. So these are the things that we don't, we don't understand in detail. If I tell you something, will you believe me? You can't see it, right? You cannot see it. So the only way in which we can answer this question is by thinking. We can't, by doing theoretical calculations. So far, the models that people have built, I don't know. This is an interesting system here. This is a strong discharge going through this cable. It's pulsating, right? So the models that people built, okay, for this is that people understand that if you go deep enough, then you can't have crystal structure. You can't have this giant big nuclei, right? The nuclei have to dissolve, and then you have neutrons and protons and electrons. This is a theoretical argument. My impression is that this theoretical argument is on solid ground when it comes to the outer core of a neutron star. Now, once you go deep inside, then you don't know, because maybe your nucleons dissolve into quarks, right? We don't know. We don't have experiments which can probe densities which are that large, right? Inside, at the center of a neutron star, you have densities which are 5 times larger than the density of a nucleus. We haven't.
These quakes are assumed to avoid that inner part of the core.
These quakes. Yeah, okay. So the quakes, in principle, the conventional quakes happen in the crust because you need elasticity to support propagation of these quakes. And that's what happens on our planet. The quakes are propagating in the crust, elastic crust of the Earth. Now, what happens in neutron star, which is not what happens in the Earth, that there are the strong magnetic fields, right? And if the strong magnetic fields are poloidal at the crust-core interface, then you launch off rain waves into the core.
strong the alpha waves are not affected by that the interface between the inner part of the core and the outer core. So
They are affected. I'll talk about this. They are affected. So we can use, if you accept this argument, if you accept this scenario, then you can really say something about this outer core, the features of the outer core. In particular, our arguments must be superconducting, or it's some strong argument for them to be superconducting. So this is this.
Which part of this argument says that the disappearing of the pulsar should be in two stages? Because first you said that it's broadened and then disappeared.
Right.
So is this clear that at which stage you get broadened and then at which stage?
So what I think happens. So this is all to do with this thing which we haven't worked out. Okay, this is number 5. So we know that you get unscreened E fields. We think, but we haven't calculated, that it will lead to discharge and then gamma rays in pairs. Now, in principle, if you have discharges in this alpha wave somewhere, this can also serve as a source of radio waves. How radio waves are made in pulses, we don't know. Okay, that's one of the difficulties in calculating this. But most theorists believe that in order to make radio waves, you have to have unscreened electric fields. So unscreened electric fields, they can do two things. And in principle, some pulsar theories will tell you they can make radio waves themselves. But they also make gamma rays and produce pairs, and they short circuit other unscreened electric fields. If you have too many pairs, then you shut off the whole pulsar.
Yeah, but
So,
if they really emit gamma rays, your model should have another predictions of same gamma rays.
right.
And then the question is that if you put exactly like a radio telescopes, could you be able to see?
Right. Now, these gamma rays don't get out because gamma rays in these strong electric fields, strong magnetic fields, as soon as gamma rays have some angle with the magnetic field line, they make pairs. Okay, so these gamma rays, they're not free streaming to the observer. In these crazy strong magnetospheres, they actually get absorbed. But you are completely right that these alpha waves that you emit into the magnetosphere, they have to dissipate somehow. And the most likely way in which they will dissipate is by producing X-rays. So we do predict kind of a burst of X-ray emission. It's not very strong. So, it's probably going to be very hard to detect, especially if you're not continuously looking. Well, maybe Dipto will decide that he wants to look at...
Then he has his own satellite.
Yeah, his own satellite, right? Continuously look at... Right. But this is a good way. See, these people, they found out things. I mean, I think this is, this whole Vela event, for me, it's a fantastic probe that we would otherwise not have. If these people didn't do this, another 20 years, we wouldn't know that these things are happening. Anyway, so let me just show you some movies. First of all, let me pay homage to the work that was done by Ashley. So this is how, so we did actually a three-dimensional seismic model of the crust of a neutron star coupled to magnetic fields. I believe that we are the first ones to do it. We did it by spectral methods. Okay, so you have some displacement psi. There is equation of motion for this displacement. So there is an elastic part, there is a magnetic part. The way in which you can simulate this motion, we found the best ways to do spectral methods. So you take this operator and you find normal modes of this operator. We have to cheat to find normal modes, okay? Elastic force is straightforward, but magnetic force is not straightforward. So in order to find good normal modes, what we had to assume about magnetic fields is that it's a split monopole inside the neutron star. And then we take the normal dipole outside, but inside the neutron star it's a split monopole in terms of what this restoring force looks like. But we have found these normal modes going between the densities of 10 to the 14 grams per cubic centimeter at the bottom of the crust, all the way to something like 10 to the 4 grams per cubic centimeter. So it's a huge range of densities. So if you want to resolve this huge range of densities, you basically need a one-dimensional Liouville problem. In order to have one-dimensional Liouville problem, these normal modes have to separate into spherical harmonics, so then you solve the radial part. If you want spherical harmonics, you have to have split monopole. You can't have a dipole field. Afterwards, okay, so this is what we do in the core. So you decompose into normal modes. These are the coefficients. We have typically in three-dimensional simulations, we have several million of these normal modes. For axisymmetric simulations, we have like 100,000 of these normal modes. We resolve the seismic waves with exquisite precision. After they propagate in the magnetosphere, you can just watch. It's very, it's a very well-tested algorithm. So then you evolve these coefficients. These are your coordinates for the system. We evolve them under the action of external force here. The external force being magnetic stresses at the interface with the magnetosphere and also at the interface with the core. So these are our external stresses. So evolve them with time. With magnetosphere, the story is different. What we do is that we consider so far only axisymmetric movements. So these are like twisting motions of the magnetar. We also consider axisymmetric magnetosphere for simplicity. In this approximation, the displacements observe these wave equations, and the field lines, the flux surfaces that we have in magnetosphere, they act as waveguides for this wave equation. Okay, so each flux surface respects its own wave equation. So we can split the magnetosphere into flux surfaces, and then we can solve simultaneously the wave equations on all of these flux surfaces. So these are the approximations that we have to do in order to have a completely solved model. So this is the result. So this is the seismic waves. Now you can see the seismic waves, once they get into the upper layers, we have this propagating relay waves from this quake. They go here. Okay, and these are the toroidal parts of magnetic fields. This is the color coding. And you see as the quake is propagating from the pole here towards the equator, you see that the magnetic fields are launched into the magnetosphere. So this is for you to have. Now this is the current that is supported in the magnetosphere. And this current can become really strong. This is the current that you need. Once this current is above what magnetosphere can support with charges, that's when you get on screen the electric fields. The quake happened at the top, right? This is a great question. This is, okay, this current is measured in terms of Goldrake-Julian current. So Goldrake-Julian density has a singularity here where omega is perpendicular to B. I think it's, this feature has nothing to do with, in reality, you don't see any particular thing here because you have certain multiplicity of these pairs, but because Goldrake-Julian density formally goes to 0 if you want to measure current in the Goldrake-Julian current, and you have this singular feature. Yeah, it's an aligned rotator, right? Yeah, it's not what happens in Vela, but that's the one we can do. Okay, smarter people in this audience can do other things, but we couldn't do. I mean, this is the first step that we could do. So this is an example of a quake which doesn't happen at the pole. It initiates at certain latitude, and you see after some time the elastic wave propagates in the crust and engages different field lines. So then you have, this is only 10 milliseconds, right? So after 100 milliseconds, the whole crust will be engaged and will be exciting alpha wave waves, etc. So now, the coupling, the poloidal fields of the crust-core interface are really important, okay? Because here what's plotted is the alpha wave luminosity into the magnetosphere. And so these are two different curves, right? One curve is when you don't have poloidal field at the crust-core interface, and then you get this red line. And basically, it doesn't dissipate. It keeps going, okay? If you want to dissipate, if you want the quake to stop after 0.3 seconds, okay, you have to couple the elastic motions through alpha waves into the core. And then you damp really efficiently. And these two figures just to show that it doesn't really matter whether you initiate the quake close to the pole or you initiate it close to the equator, because elastic waves propagate through the crust and engage essentially all the field lines. You know, this basically is invariant with initial configuration of this quake. Now, the damping timescale, the timescale to damp elastic motions into the core actually can be estimated analytically, and this is the mass of the crust, okay, divided by the density of the core, the alpha wave velocity, and the area, okay. Almost dimensionally, you can write down this expression. And of course, we have calculated it exactly, but this is how things scale. So what is really important is this alpha wave velocity, okay. And you have broad pulse, you have missing pulse, and then you have normal pulse again. So you have to do all this in something like less than 0.3 seconds. And the damping time scale that we get for Vela parameters, okay, assuming that you have about the same field, poloidal field at the crust-core interface as you have for the dipole component that we see from the Vela spin down, the damping timescale we get is of the order of 200 milliseconds. Now, there is a very important ingredient that I want to talk to you about, is that if the core is non-superconducting, this is what the field lines will look like, okay? If the core is superconducting, the superconductor expels field lines into islands. If the superconductor is type 2, then these islands are small and these are flux tubes. If the superconductor is type 1, then these are domains. But the main thing is that the field lines in these islands and these flux tubes are bunched together, and the intensity of the field in these flux tubes equals to the critical field of the superconductor, which is 10 to the 15 Gauss, right? Now, Vela itself has a field of about 2 times 10 to the 12 Gauss. So the field, 10 minutes. Oh man. So the field inside this flux tubes is something like, factor of 300 or 400 stronger than the field here. So it's a really strong concentration of field lines. What does this mean? Remember, the stresses of magnetic fields scale as b squared, right? So if you take your flux and you bunch it into islands and you find the average b squared, it goes up by the factor by which you bunch, right? So the stress here goes up by effective tension here goes up by a factor of 300 or 400. So it's really significant. The superconductor makes a lot of difference.
On this point, the rho VA is where? In the core?
In the core. Because, so here I'm the crust, right? This is the magnetic field line. I'm vibrating and I'm launching the alpha wave, right? The alpha wave propagates into the core. The boundary condition for this alpha waves is my amplitude, the amplitude with which I'm moving up and down. And then, that's the boundary condition. But then you have to calculate the amount of energy which is radiated into the core.
So that's what allows the damping time to go down, is the concentration.
That's right. That's right. So the alpha speed, the tension goes up dramatically. The density goes down. Okay, so yes, there is a factor of 300 or 400 increase in the stress, in the tension of these magnetic field lines. but the density, so the density goes down a little bit. So these field lines are not as loaded. Why? Because of the protons are superconducting, they are not dragging neutrons with them. Okay, neutrons are decoupled. So essentially, this alpha wave only involves protons, which are typically, 20% of the total mass at the outer core, or 10% of the total mass. So, but it's this effect that allows us to bring the damping timescale down to something like 200 milliseconds.
Is it easy to say why it's the mass of the crust rather than the mass of the core then?
So the elastic energy, okay, is contained here in the crust, right? So think of the crust as an oscillator, right? Roughly speaking, the energy of this oscillator is the mass of the oscillator times the average V squared of the oscillator. And then you drain it by this channel. So, yes?
So the fact that it's out for a couple of periods is really just a coincidence, that like it's not tied to the time scale of the pulsar. In other words, if we saw another disturbance in one, you might not see the disturbance at all, or it might be for many periods.
That would actually be the prediction of this, right? But so far, Vela is the only thing that we've measured. You have to understand that before this measurement, we are completely ignorant what happens during the glitch. So typically, the way pulse observations take place is that, you get time on a telescope. If you have a reason to time something frequently, okay, you get time once per 2 weeks. You time this pulsar for an hour, right? And then you come back 2 weeks later. So, it's you only see the glitches after effect, right? After several weeks, you see that something happened, right? That's why you never, hardly ever resolve the glitch. And this is a really unique set of data. Right, but this is a very good point. Okay, so...
It's also unique because it's bright enough that you can see the individual pulses.
Bright enough you can see the individual pulses, right? So, okay, so I hope that I have convinced you that at least in the case of Vela, we have some circumstantial evidence of this glitch that it has some significant poloidal component of the field that penetrates the core. So the observations are consistent with superconducting protons in the outer core. In principle, you could have them not superconducting, but then you would have to have the field at the crust-core interface about a factor of 5 stronger than the surface field. In principle, there can be some buried fields inside a neutral star. To me, it sounds a little bit unnatural, but I think we have to keep an open mind.
Excuse me, the denominator, when you have superconductor and you just shrink the area of each of the lines, area would also decrease.
So
this is like a accumulation effect of like a multiplication effect of the velocity times a that could either increase or decrease.
no, the way to think about this is that you have to average. You can't just say you can't just say only the flux tubes, become part of the alpha n waves.
But then, imagine that
It's-
you don't have superconductor that are always spread over the sphere, but now you just shrink it to some lines basically.
Yeah. So if you're thinking about this picture,
Yeah.
if you're thinking about this picture, it is incorrect to think that if you shake the crust, only the material within this flux tubes will take part in this motion. All of the protons will take part in this motion. And this field lines, once you have macroscopic motion of the field lines of the flux tubes, the protons follow. So if you're thinking about this formula, the correct thing to do is to find, to average the tension in these flux tubes over the whole area, right? So, sorry. Yes, you average the flux tubes over the whole area. You average the tension in the flux tubes over the whole area, and then you, B squared, basically, right? You average B squared. But because your B is a factor of 300 greater inside the flux tubes, B squared is a factor of whatever, 10,000 greater. right, inside the flux tubes. And you dilute it by averaging it over the whole area. So that's the correct procedure. Okay, so I think I should finish. So this is, the conclusions are that I think this is a remarkable event, which tells us something about the neutron star. We certainly should think about this very hard. There is a working hypothesis that we are working with, so that it's a crust quake that flood magnetosphere with plasma, etc. These observations do constrain, if you believe this picture, okay, if you take this picture as truth, these observations do constrain the internal magnetic field structure of Vela pulsar. Now, from my point of view, there are several weak points in this model. So before you ask questions, let me point out what, from my point of view, the weaknesses are. First of all, we do not know the origin of this quake. I cannot, the phenomenology smells of the quake, but I cannot come up with convincing reason of why this quake should be there in Vela. There is no like super strong magnetic field that can break the crust or anything like this. So it must be something that we don't understand. We did not yet include the dissipation of Alfvén waves in the magnetosphere. So we found a way, a reasonable way, I think, to damp the motion of elastic waves in the crust. So this happens on a time scale which is in complete agreement with what conventional theory would predict. But we still have to understand how the Alfvén waves in magnetosphere damp. And this is not a trivial problem. With this, I want to ask you if you have any questions about Vela, and I don't think I have time to talk about another topic. I think people should just, yeah, am I supposed to point? What's the tradition here?
Does your model predict any heating of the crust of the pulsar?
Yes. Yes, right. So this energy that is released into the magnetosphere, this energy has to come out somehow. And I think my own bias is that it has to come out as X-rays, because like I said, gamma rays are observed, and typically X-rays is something that can propagate out. But the intensity of this X-ray burst is not very big, so it will be hard to, I think it will be hard to see. Possible if you are looking at that very moment, at that.
You showed a graph which had the y-axis was L, which I thought was luminosity.
Right.
Which was fairly high. What was that?
But for only a small period, for only a small duration of time, right? This is luminosity in Alfvén waves. Right. So let me see. Right. This is the luminosity in Alfvén waves, but it dissipates very quickly. So it's the overall energetics of the burst is quite small. So if you imagine that all this luminosity comes out in X-rays, it's still. But I think Deep2 should look, but I don't think it's going to be easy.
Well, there was a glitch 20, 30 years ago, which was observed, I think, by Rosat. They were lucky; they got an observation just before the glitch and just afterwards. No increase.
But when you say just before and just after, do you remember the time?
Days.
Okay. No hope, days. You really have to look at that very moment. I also think, by the way, that heating is important. Sorry, this is a little different. I think heating is the way in which a quake can trigger a glitch. So, for example, if you have a quake, and there are models by Lincoln Epstein that the quake locally where it happens heats up the crust, and then the vortices are able to creep. They don't mechanically unpin, but they're able to creep, and this creeping motion can spin the star up. So I think from this point of view, from the theoretical point of view, heating is also a good thing to think about in the context of a glitch. But in terms of how much you can see from this type of luminosity in alpha-wave waves, I think that's going to be hard. Sorry, Deepta, you want to go?
I think the question that Fred was getting at is whether the energy release is enough that you would actually change the thermal properties of the crust. So that if you could get to some way where you didn't have to be looking right at that instant.
Right.
Right. So it doesn't seem though that the energy you're talking about would be enough to really change the temperature. It wouldn't change the cooling of the neutron star.
That's a great question.
So
We haven't calculated it. Honestly, we haven't done this calculation. But
what you're talking about, it's not
but my impression it's going to be small.
yeah. Okay. So to see the evidence of this plasma being injected, you'd really have to be looking in X-rays or whatever right at that.
That's
right.
right.
At that instant.
I think so.
Right. That's what you're saying.
The luminosity of the Vela pulsar is what, 132? So this is, briefly, it's,
Well,
big
but
increase.
in our thing, right? So I'm not sure.
But let's say, I mean, let's suppose all of this comes out as X-rays on the same time scale, right? Would you be able to develop,
Maybe. I mean,
see
yeah,
such transient event?
yeah, maybe, but-
But you have to have some instrument which is pointing at Vela at the same time, right?
Well, first we have to have some instruments. That's the first thing. I totally agree. So, I guess another question I have is, so the observations that you're talking about are radio pulse observations, but
Right.
I could imagine that making this using a plasma would make some non-pulse radio flash at that time. Right. So if their telescope is in any way sensitive to imaging and not just to timing, they might have the ability, because Vela glitches every once in a while. So if you were to pick a source that glitches commonly, even like once a year like that, and to prepare to stare at something for years, then that's great. So use this. If they could observe in a mode where they could see a change in the radio flux, they might see radio flare that happened at exactly the same time as a glitch.
If they have some wide field instrument, you mean
No,
in the
I mean,
same?
They're pointing at this.
Oh, they're pointing, right.
Right. So I just don't know whether they have the. It's different. I don't know whether they have the imaging sensitivity because it's a change in the DC flux, right? So the way they're making the measurement, they're just looking at the pulsation. I don't know whether they have. I don't know if there are any radio observers who could comment on this, but it's that might be a way you could do it, right? Because it seems like changing the plasma properties, even just over that instant, should give you some change in the. Since it's not tied to the rotation of the neutron star, there should be some change in the radio flux that's unpulsed, but impulsive because of the plasma injection. I just don't know whether they had the sensitivity to do that, because you'd have to be able to detect that change over half a second.
Yeah, that's a great question. I don't know also.
Last question, Gus. Do you expect there to be any time delay between the glitch and the X-ray burst on like the order of the damping time scale?
I think it should be small. Honestly, my own bias is that the damping has to happen quickly, because the pulses return back to normal after basically 3 rotational periods, which is 0.3.
Was it normal? To my eyes, it looked like the shape changed a bit.
Yes, that's very well spotted, actually. That's very well spotted. So let's look at the data. I had the same thing, Ramesh. So now in the paper they say the following. They say if you find a timing residual for each pulse, okay? The timing residual for each pulse, you do it by taking this template and beating it against a single pulse, basically sliding it and seeing where you get the biggest overlap. You mark this timing residual, it's a number. Let's say this timing residuals, they jump around a lot before this event, okay? After this event, they say it's much more stable, this timing residual, for about 2 seconds, so 20 pulses. It's much more stable. It wanders much less. This is one thing. Another thing they say is that they see also much less variability in linear polarization of these pulses. So it may be, I don't know what to make of it.
But the profile itself is not changing.
They don't say it's changing significantly.
Because I look at the last guy before.
Yeah.
It's kind of a sharp rise and slow decline.
Right.
The first guy after is just the opposite.
No, I see what you mean.
But it's very common in radio pulsar stuff that the average pulse is very stable. The individual pulse is very low.
Right. But also remember this. Yeah, this pulse, this telescope was not as sensitive. Like the Parkes profile looked like spectacular. These ones are,
Okay, I'm afraid we have to clear the room, so let's thank Yuri again. Beautiful stuff.
Thank you.
So I'll look forward to talking to you this afternoon. I mean, I'll be at lunch, but
Okay.
we have half an hour this afternoon.
Okay,
I wanted
good.
to ask another quick question.
Sure.
I'm interested in low-mass neutron stars.
Uh-huh.
And,
How low?
well, in theory, you go from 2 solar masses down to about 1/10 of a solar mass.
Uh-huh.
When you get below about 0.5 solar masses, the star starts to swell.
Uh-huh.
And one thing that's happened is the crust becomes more important as the
Right.
mass decreases.
Right.
Well, you're down to about 0.4 solar masses. The volume of the crust is maybe 5 times the crust on a 1.5 solar mass star. So when I hear people say that the magnetic field of a magnetar is confined to the crust, I think there's a lot more room for magnetic field
Right.
in a low-mass neutron star.
That's right.
I wondered if that would...
Well, that's an interesting question. I haven't thought about this. I haven't considered it. Is there any context in which you can imagine that you would form such low mass neutron star?
Yes, I can imagine it,
You
but
can imagine?
everybody disagrees with me.
Oh, okay.
There is a pulsar that's headed away from a supernova remnant. It's MSH 61A, I think.
Sorry, I probably have to get out.
It's moving very rapidly.
Uh-huh.
Okay, so here's a candidate for something of low mass. The pulsar has a jet on it which illustrates the direction of the pulsar.
Are you rushing us out?
Oh, no. I actually, so we wanted to talk to you. So, Flora and I, my name is Lika.
You're Lika, okay.
Yeah, hi.
Hi, Yuri.
Nice to meet you.
So let me answer the question, and yeah, I have an appointment with these girls.